An introduction to chemical reactions begin by reminding us that an equation is used to represent a chemical change. So let's go back from our very first chapter where we understood the difference between chemical and physical changes. Remember, a physical change alters a physical state of a substance, but it does not change the identity. It is exactly the same in chemical composition as it was before. Now, as an example, if we were to take water in the solid phase and allow it to melt to go to a liquid phase, notice that we have the exact same chemical identity. Water is on the left as H2O, water is on the right as H2O. So the same chemical identity on the left and the right, all that's happened is a phase change. The solid melted into the liquid water. A physical change, just as an example, would still have water molecules, two H's bonded to an oxygen, two H's bonded to an oxygen, and all we did was allow those water molecules to become, at a higher energy state. Notice that these are more randomly organized. The liquids have an ability to flow, and yet it is still the exact same chemical composition. And that's the clue. That's really the key for a physical change. Alters the physical state, but without changing the composition. On the opposite side of that would be a chemical change. A chemical change converts one substance into another. So we create new compounds. That the resulting products are very different in chemical and physical properties than what we started with. Chemical reactions involve breaking bonds in the reactant side and forming new bonds on the product side. Reactants are the starting materials. Products are the ending materials. The reactants break bonds. So we can see this definition. The reactants are the starting materials, and the products are the ending materials. We say things such as reactants yield products, reactants go to products, reactants form products, whatever you want for that arrow. A chemical reaction involves breaking bonds in the reactant side and forming new compounds on the product side. Let's take a very specific example. When I look at this molecular model, notice that inside of this reactants, I have a methane molecule, CH4. That methane molecule, I see 1, 2 of those. This unit, this little value here is going to be called a coefficient. It's telling us how many methane molecules are the starting materials. And do you see that molecular art gives us 2 molecules of methane? I also see, now see that plus sign? I also see 1, 2, 3, 4 molecules of molecular oxygen, O2. Notice these starting materials are what we call reactants. They're beginning materials. Then I see the arrow, and this means yields, forms, produces, goes to, makes, all kinds of different words to represent the reactants are going to change into something else. Well, what else do we see? On the product side, we see completely new compounds. I see carbon dioxide, 1, 2. Notice I'm going to put a 2 in front of a carbon dioxide to let you know there's 2 molecules of CO2 that formed. Then I see a plus to separate the 2 products, this and that, so a plus sign. And now I'm counting 1, 2, 3, 4 molecules of water. The ending products are very different in their chemical composition as the reactants. Reactants yield products. Notice the methane and oxygen converted into 2 completely new substances called carbon dioxide and water. And coefficients are used to balance a chemical equation, which we'll learn means to have the same number of each element on both sides. That's really obeying the law of conservation of mass, which we'll say is you cannot destroy matter or create matter. All you can do is convert it from one form to another. So we use coefficients to make sure we can account for all of the starting atoms on the product side. And so that's where we're counting each individual element. And we will practice balancing equations. Plenty of practice coming up. But now this skill is just trying to remember, is this a chemical change or a physical change? Can we represent those following reactions, or are they a physical process? So let's take a look at the molecular art in letter A. I have a molecule where two atoms of a blue, well, the blue atoms are bonded together to create diatomic molecules. And I have over here two molecules of a diatomic red atom, right? So two atoms of the red ball bonded together. So I could just say I have two, and let's just use B to represent the blue, and there's two molecules of B2. And on this side, there's two molecules of a red atom bonded together to make a diatomic molecule. What else do we see over here? Well, now look, all of these have switched partners, haven't they? Now I have a blue bonded to a red. So I'm going to let that be represented by blue-red in terms of the molecular model. This indeed represents a chemical change because these bonds had to break. So these bonds over here were broken. I broke those guys apart. And that's the very definition of a chemical change. Bonds were broken, and over here, new bonds formed. Now let's take a look what we have here. Inside this molecular model, looks like we have a red, looks like water, doesn't it? A red attached to two whites. That's a water molecule. And it looks like they're still just kind of in a liquid form, where I can see they're close together, but they're randomly displaced, right? So that would be in a liquid phase. And over here, it's the same structure where I have a oxygen bonded to two hydrogens, same compound, but now they're very far apart, which would represent the molecular phase of a gas. So really, we've just gone from liquid to a gaseous phase, which is a phase change. It would be called evaporation when a liquid converts to a gas. So this we would represent as a physical change. And this last one looks like it just became more ordered. So this would represent a liquid phase where the molecules are still close together, but in a random order. And over here, this represents a solid phase where they still have the same atoms, but very ordered. So when a liquid converts to a solid, that's called freezing. We could represent this also as a physical change. So the only chemical change with those molecular models was the first in letter A. So we've learned that a chemical reaction can be denoted through a chemical change. In this example, I see a molecule of H2O2. That's called hydrogen peroxide. It might be in your medicine cabinet at home, hydrogen peroxide. And I see that it undergoes a chemical change and it starts to bubble. Do you see in this hand, there are bubbles coming out, and that's evidence of something new. Now, peroxide will spontaneously decompose, and we're going to learn that decomposition is one of our 5 general patterns of chemical change. When hydrogen peroxide decomposes, you see that a water molecule is released, and it generates oxygen gas. And we'll learn that that little G is going to represent the gaseous phase. The AQ, we'll learn, will represent dissolved in water, aqueous. And we'll learn that the little L I've used here represents the liquid phase. We'll also learn that this equation is not yet balanced, and you'll hear me call those a skeleton equation. One that is completely written in terms of correct formulas on the left for the reactants. And I have the products over here on the right-hand side, but it's a skeleton because it's just not yet balanced. And when we learn how to balance equations, I'm going to model those with a T-chart. And for a T-chart, you'll hear me say, let's represent the left side and the right side of our arrow. The left side meaning the reactants and the right side meaning the products. And we have two elements we have to account for in this equation. We have H's and O's. And I just have to count. On the left side, I see a total of 2 hydrogens, and I see a total of 2 oxygens. On the right side, the product side, I can count 2 hydrogens, but now a new combined total of 3 oxygens. 2 from the molecule O2 and 1 more from the molecule of water for 3 total atoms. So clearly you see it's not yet balanced because I can't just automatically invent another oxygen. It had to come from somewhere. So we'll learn that coefficients are going to be required to balance these. And when we learn to place a coefficient in front of a reactant or product, we have to retabulate every time we change a coefficient, because the coefficient of 2 distributes throughout the entire compound. It speaks to both the hydrogen and the oxygen. So now let's retally. Hydrogen, 2 molecules, each with 2 atoms of hydrogen, now gives me a total of 4 hydrogens. Same with the oxygen, 2 molecules, and each molecule has 2 O's. That's a total of 4 O's. And now when I recount, over here, I'm going to need to adjust the hydrogens. And so when I fix my T-chart, 2 times 2 is 4 oxygens, and we have 2 plus 2 more is 4 oxygens. So we've just balanced our first equation, representing all kinds of good vocabulary words. Reactants turn to products. The reactants are the starting materials. We write out what's called a coefficient in our balanced equation to help obey the law of conservation of mass. So this chemical equation uses chemical formulas and other symbols showing what reactants are the starting materials in a reaction and what products are formed. To define a chemical equation represents a chemical change. Reactants are written on the left. Reactants are the starting materials. The starting materials have their bonds broken as new materials form. The ending materials are known as the products, and the products are on the right side of our arrow. And we said these numbers that we place out front are called coefficients. The coefficients show the number of molecules of a given element or a compound. Coefficients are used to balance equations. They're used to obey the law of conservation of mass. Coefficients are these whole numbers written out front to tell us how many molecules, or we'll also learn to tell us how many moles are present. When I read this balanced equation, I see one molecule of CH4 reacts with 2 molecules of oxygen to form 1 molecule of carbon dioxide and 2 molecules of water. And do you see how I'm using the word molecule to represent the unit that a coefficient is giving us? How many molecules of each reactant and product are needed to balance the equation? That's the job of the coefficient. And we use these coefficients, we said, to obey the law of conservation of mass. And we're asked to define that term and just simply say atoms cannot be created nor destroyed in a chemical reaction. Atoms cannot be created nor destroyed. All we can do is rearrange them in terms of reactants turning to products. And that's the purpose of a coefficient, is in accounting. We want to account for all of the different atoms that we started with to make sure we end with the same number of each atom. So what does it mean to have a balanced equation? It means we have the same number of atoms of each element on both sides of our equation. Let's count together. In this example, let me just go through this with you. In this example, you have typed on your page, looks like this. CH4 plus 2 O2s yield CO2 and 2 H2O. We're being asked to just account how many atoms of each are present in the equation. And this is where I encourage you just to think about a left-right chart, a T-chart I call it. Notice we have 3 different elements we're counting. We have a carbon, we have a hydrogen, and we have an oxygen. C's, H's, and O's. The carbons are represented in red. I see 1 atom of carbon on the left, and I see 1 atom of carbon on the right. Notice the hydrogens are written in black. So here I see a total of 4 H's. And over here I see 2 molecules of H2O. Now think about what that means. It's like writing H2O twice. That's what the coefficient of 2 means. 2 groups of water. How many total hydrogens? Well, there's 2 in the first molecule plus 2 more in the second molecule for a total of 4 hydrogens. And now let's count oxygens. Here we have an oxygen molecule, but we have 2 of them. That's what the 2 in front of here means. 2 groups of O2. That gives me a total of 4 individual atoms. Here's a molecule with 2 oxygens. So that would be like writing carbon dioxide just once. Each carbon dioxide has 2 atoms of oxygen. And remember, writing 2 groups of water gives me 2 more oxygens. So there's a total of 4 oxygen atoms. And that's what we tallied there. 1 carbon, check. 4 hydrogens, yes. 4 oxygens, yes. Since we have the same number of each element on both sides of our arrow, we know that we've obeyed the law of conservation of mass and that we've balanced our equation. Now, when we practice balancing equations, the skill here is to really understand how to count atoms. That's what we're practicing now to take a next step in deciding what coefficients we need as you're given an unbalanced equation. So the first step is to simply count. This is a pattern of chemical change where I see a hydrocarbon reacting with oxygen, forming carbon dioxide and water. We will learn that this type of chemical change is known as a combustion. Did you notice this was also a combustion on the previous slide? We had a hydrocarbon reacting with oxygen to form carbon dioxide and water. We have a hydrocarbon, which really is just a type of fuel that you burn in oxygen and you form carbon dioxide and water. It will be one of the 5 patterns of chemical change that we write about in our notes here shortly. Taking a fuel consisting of hydrogens and carbons and other elements such as an oxygen in this example and burning it. That's known as a combustion. Now let's count. Let's create a T-chart. And so we can tally how many atoms of each element there are on the left side of the arrow and on the right side of the arrow, reactants and products. There are 3 different elements present. I can count carbons, I count hydrogens, and I count oxygens. C, H's, and O's in this combustion example. So notice that the highlighter that I'm going to use is going to place a highlighted mark over what we call coefficients. And coefficients distribute through the entire compound. It's telling us how many of each molecule we have. These are very different than what we call subscripts. Subscripts sit next to individual elements, telling us how many atoms we have within the compound. Coefficients distribute through the entire compound. So, when we count C2H6O, that is one molecule of C2H6O, and inside that molecule, I count two individual carbon atoms. Inside this one molecule of C2H6O, I can see 6 individual hydrogen atoms. And I see 1 oxygen. I also have 3 groups of O2. It's like writing oxygen 3 times. Each individual molecule is composed of 2 oxygen atoms, so that's a total of 6 atoms of oxygen, plus the 1 more from this particular molecule gives me a total of 7 O's, 7 oxygens on the left-hand side. Let's do the same tallying on the right side. Here we have a coefficient of 2, which is communicating all the way through that molecule. Carbon dioxide, well, there's 2 of them there, so each individual carbon counts to 2. 2 times 2 is 4 for the oxygens, plus 3 more from the water, giving us a total of 7 oxygens. And 3 times 2 gives us a total of 6 in terms of the hydrogen. Can you visualize that? Visualize what these coefficients mean. We saw a coefficient of 1 in front of our molecule. Notice that's our fuel, our hydrocarbon that we are combusting. It contains 2 carbons, 6 hydrogens, and an oxygen. And to burn it, to ignite it, we had 1, 2, 3 molecules of oxygen. For every 1 molecule of the fuel, 3 molecules of oxygen were required. Now notice, bonds broke on the reactant side, and new bonds formed, creating new compounds. So the very definition of bonds breaking and new bonds forming is a chemical change. We had 2 molecules of CO2 form. We had 3 molecules of water, 3 H2Os. But when we're balancing equations, we're counting individual atoms. Let me model for you what I mean. Here's the 2 carbons right here. Here's the 2 carbons right here. Carbons are balanced. 1, 2, 3, 4, 5, 6, 7 oxygens. 1, 2, 3, 4, 5, 6, 7 oxygens. Perfect. And here we have 1, 2, 3, 4, 5, 6 hydrogens. And on this side, 1, 2, 3, 4, 5, 6 hydrogens. We have indeed balanced our equation. So coefficients allow us to obey the law of conservation of mass. We count individual atoms to make sure that there's the same number of each element on both sides. Coefficients tell us how many molecules we have of each reactant and each product. It's time for you to practice. Turn off the video for a moment and just count how many atoms of each element in these balanced equations, and then come back to me when ready to check. Welcome back. In letter A, this is a very familiar equation from a slide ago. This is the one that we were looking at where hydrogen peroxide decomposed. Notice I'm going to say this is a decomposition reaction, just so I can see a little bit of a lesson coming up. To decompose means I take a compound and break it into smaller pieces, right? To decompose, we have one reactant turning into more than one product, right? You're breaking it down into simpler pieces. So that pattern of chemical change, we'll learn. Decomposition, what makes it unique is it has just one reactant breaking down into many products. We're just being asked to count in this example. There's two different elements to count. We have two groups of H2O2. So just thinking about what that means, two molecules of H2O2 that connect HOOH. So how many individual atoms did you count? There's 1, 2, 3, 4 hydrogens and 1, 2, 3, 4 oxygens. So on the left side, there's 4 of each atom. 2 times 2 is 4 for both of those atoms. Now let's consider the right side. We have a water molecule form, and there's 2 of them there. 2 H2Os, and we have an O written as an O2 molecule. So just kind of thinking about what balanced means. When I count, on the left side, I count 1, 2 oxygen atoms, and I count 1, 2, 3, 4 hydrogen atoms. Over here, 2 more oxygens. So let's tally up what we have. The number of H's, 1, 2, 3, 4. The number of oxygens, 1, 2, 3, 4. We have 4 atoms of each element. The reactants turn to products when we balance our equation. Same number of each atom, we had a decomposition reaction occur. Let's look at letter B. I notice that I have a hydrocarbon. Hydrocarbon is an element composed of carbons and hydrogens. This would be called a fuel. It's an octane. Hear that oct for carbon 8? We see that it's being placed in with oxygen. Out comes carbon dioxide gas. And another product was called water. We are learning that this represents a pattern of chemical change known as a combustion reaction, where we'll learn when a hydrocarbon burns in oxygen, it releases carbon dioxide and water and a whole lot of heat energy. But now our skill is to practice counting. Let's create a T-chart that represents the left side of the arrow and the right side of the arrow. We have to count carbons, we count hydrogens, and we count oxygens. Those are the 3 different elements presented in our equation, C's, then H's, then O's. 2 to 25 to 16 to 18 is our coefficient ratio. That tells us how many individual molecules we have. Well, when I look at carbon, carbon has 2 groups, and there's 8 within each, so that's a total of 16 carbon atoms. When I count hydrogens on the left, there's a coefficient of 2 times 16. Oh, Linda. That's an 18, sorry. I had 36 in my mind. And for oxygen, the coefficient of 25 times the 2 atoms in each molecule gives us 50 oxygens. 16 carbons, 36 hydrogens, and 25 times 2 is 50 oxygens. Let's count the right side. For carbon, the coefficient of 16, and that molecule carbon dioxide just has 1 carbon in it, so there's 16 carbons. For the oxygen, just because it's in next, we have 16 times 2 from the carbon dioxide plus 18 times 1 from the water. 32 plus 18, oh, that's 50. 50 oxygens on the right side as well. Let's do the hydrogens next. Looks like there's 18 waters Each of those has 2 hydrogens, so that's 36 hydrogens. We are indeed balanced. Same number of each atom on both sides of the arrow. Perfect. Let's look at letter C. Reading this out, we have sodium phosphate. Hear that name of the polyatomic ion chart? Sodium phosphate reacts with magnesium chloride. Every time I can practice nomenclature, I will, because it's an important skill to keep practicing. Now on the product side, I see magnesium phosphate, PO4 is the polyatomic ion called phosphate, and sodium chloride. Now there was a reason I wrote all of that out, and I hope you are as well. Sodium phosphate reacts with magnesium chloride to form magnesium phosphate and sodium chloride. What I'm seeing here is the pattern of chemical change we will learn is called a double replacement, the double displacement, a double exchange. All of those are the correct category. You'll hear me call it a double replacement. See the 2 positive ions, sodium and magnesium? When I bring my eyes to the 4 characters here, I have a sodium connected to a phosphate, magnesium connected to a chloride. What happens is the 2 positive ions exchange partners. Magnesium now goes with phosphate, and sodium, oops, he should have been blue. And then sodium, who I color-coded yellow, went to the chloride. A double exchange. The sodium goes to the other partner's last name, chloride. Magnesium will go to phosphate. Sodium goes to chloride. Magnesium goes to phosphate. And we'll consider charges when we practice this double replacement pattern as we predict out new formulas. An old double exchange, the 2 positives exchange partners. But right now, as I seed the next lesson with practicing, right now we're practicing counting. Alrighty, so letter C, let's count. We have a left and a right side. There's 4 characters really. We're going to count sodiums. We'll count individual phosphorus and oxygens. We'll count magnesium, and we'll count chloride. And I'm going to change my mind, and I'm going to show you why. I'm going to leave the polyatomic ion phosphate as a group. And this is a great trick when you're learning to balance equation. Because I can see on the left side phosphate, I can see it on the right side phosphate, that group of atoms acting as a unit, carrying a charge. Let's just leave it as a unit. So the number of sodiums, I can see there's a coefficient of 2, and there's 3 of them in there, so 2 times 3 gives me 6 sodiums. When I have a coefficient of 2, it talks through the whole compound, so 2 groups of phosphate as well. There's 1 unit of phosphate, but there's 2 sodium phosphates for a total of 2 PO4s. On the other reactant, we have MgCl2, so 3 times 1 gives me 3 magnesiums, and 3 times 2 gives me 6 chlorines. On the opposite side of the arrow, I can count 3 magnesiums, that's balanced, 3 on both sides. I can count 2 groups of PO4, that's balanced. Notice this PO4 is taken twice, so that's 2 units of PO4. Coefficient here is 6 for the NAs, that's balanced. And 6 times 1 is 6 chlorides, and that's also balanced. We've proved that each one of those obeys the law of conservation of mass. And so I'm proud of you for counting. It might seem so easy, or it just depends on the number of background practices you've had, how easy or how difficult the skill is. And so if I'm over teaching, I'd rather do that than assume we know. So the big skill of this very first practice is to just make sure you understand what the coefficient is doing to the equation. If a term has a balanced equation, it has a coefficient of 3 in front of the formula, Al2SO4 taken 3 times. This is called aluminum sulfate. Aluminum has a fixed charge of +3. Sulfate is a -2. So you can see when they crisscrossed, we had Al2SO4 taken 3 times. Aluminum sulfate. How many of each element do we have? Well, I have an aluminum, I have a sulfur, and I have an oxygen. If I were going to balance, I would probably leave the sulfates together. If on the product side, they're all together as well. Now, aluminum, there's 3 molecules, and each one of those molecules has 2 in it, so that's a total of 6. There are 3 molecules. Notice that the sulfur has just a coefficient of 1, but it's taken 3 times. It's like writing sulfate 3 times. So what if you had 3 SO4s? What does that mean, that coefficient? Times. 3 groups of SO4. That's what this means. Now the coefficient of 3 says you have 3 sets of those. So that would be 2 sets. And here's 3 sets of SO4. The coefficient of 3 and the subscript of 3 are both taking account to tell us there are 9. 3 times 3 is 9 sulfurs. How many oxygens? Well, count how many oxygens there are and you'll see 1, 2, 3, 4, 5, 6, 7, 8, 9 groups of sulfate, and each one of those has 4 oxygens in it. So to kind of calculate that, you'd have 3 groups. Each one has 4 oxygens, and they're taken 3 times. 12 times 3 is 36 oxygen atoms. So what this tells us, the coefficient of 3, and this would tell us the parenthesis taken 3 times. Three units of aluminum sulfide contain 6 atoms of aluminum, 9 atoms of sulfur, and 36 atoms of oxygen. We have to be able to distribute the coefficient, knowing that the parenthesis says taken 3 times, meaning that you're writing out sulfate 3 times for each aluminum sulfate. And then 3 of those multiplies it again by 3. This is very challenging, so it requires practice. Keep practicing counting atoms. You know, we have some other chemical symbols that we can place into our chemical sentences just to kind of give them even more flavor. So for instance, if I'm writing a chemical equation and I come across an arrow from left to right, you know that that means it's a reaction arrow. If you see an arrow with a triangle on top of it, you'll know that that reaction is being heated. In order to decompose compound AB, you might need to heat it. So you'll see a triangle across the top of the arrow. The solid, liquid, gas, and aqueous phase are additional adjectives that you can place next to these symbols to let you know the phase of matter. If something is dissolved in water, it's an aqueous solution. So if I have, let's say, table salt as an S, or table salt as an AQ. You now get a better feel of how the conditions are for the equation. This, of course, would be in a solid form. Just think of little salt crystals coming out of your salt shaker. A solid form of sodium chloride, where you have a very three-dimensional crystalline structure. But table salt also dissolves in water. So this would be salt water in a solution. So now you know it's occurring in water. Salt water, NaCl, AQ. Well, here we are again, Mrs. Hanson here, beginning with section 5.2, thinking about how to write a balanced chemical equation. We know that an equation depends upon having the correct formulas of both reactants on the left and products on the right. When we balance an equation, we use what are called coefficients to balance one element at a time. Remember the cardinal rule, never ever change a subscript in a formula to balance an equation. And finally, at the end, you want to make sure that your balanced equation is using the smallest sets of coefficients possible. Coefficients are always whole numbers, and they're in the lowest ratio possible. The best way is to just dive in and practice. Let's begin by writing out a balanced chemical equation from these words. Alrighty, so propane gas. Alright, so propane is given a C3H8, and I'll just add that little adjective G to let you know that the phase of matter of propane is in the gaseous form. Propane is that fuel you use in perhaps your gas grill at home when you light up to cook a burger on the grill. You're lighting propane. Here we see reacts with. That's going to be the plus sign, reacting with. Remember, oxygen from the air. Oxygen is one of the 7 diatomic molecules you need to memorize. Diatomic means oxygen never exists as just O, but it exists as a diatomic molecule. And I'll put little gas because I see it's from the air. The next words I read are to form, and that's the arrow. It's forming carbon dioxide gas. Then I see the word and, which is the plus sign. Water vapor. Water is H2O. The vapor is the little g for gas. I'm going to encourage you as you practice to give yourself space to let you remember where the coefficients go. Never put a coefficient in between a compound's formula. Always place it out front so it speaks to the entire compound. When we begin practicing, do you remember? This is known as a combustion pattern. We have a hydrocarbon fuel called propane, burning in the air with oxygen, forming carbon dioxide water, known as a combustion pattern. One of the 5 that we'll write down in our note packs. Let's create a T-chart to tally how many C's, then H's, then O's. And when you balance combustions, the best advice I can give you is get the carbons first, then the hydrogens, and save your oxygens for last. Let's count. On the left side, I can see a total of 3 carbons. I can see a total of 8 hydrogens. And I see a total of 2 oxygens. Individual atoms of carbon, H's and O, have been tallied. Do the same on the right side. I count 1 carbon, I count 2 hydrogens, and a combined total of 2 plus 1 more from the water is 3 oxygens. Remember that oxygen now is appearing in 2 separate places, so I have to combine the total to 3. Starting with your carbons, let's place in a coefficient and balance the carbons. I need a coefficient of 3 on the right-hand side to have 3 carbons. Fix your T-chart, because not only did you change the carbons, you also changed the oxygens. So no longer is there 3. There's 3 times 2, which is 6, plus 1 more yet over on the water. So that's a total of 7 oxygens. Carbons are good. Let's go down to the H's next. If there's 8 hydrogens on the left, let's place a coefficient of 4 in front of the water so that we can see 4 times 2 gives us 8 hydrogens. But fix your T-chart because you've also changed the number of oxygens. You have 3 times 2 is 6 from the carbon dioxide, and 4 times 1 now, which is the number of oxygens in the water. So we have 6 plus 4 gives me a total of 10 oxygens. Now I can back up to the left side, placing a coefficient of 5. 5 times 2 gives me 10 oxygens. We know we're balanced by using the T-chart method, counting left and right. Our coefficient ratio reads 1 molecule of propane reacts with 5 molecules of oxygen to form 3 molecules of carbon dioxide and 4 molecules of water. Our balanced chemical equation. We can try another together. Write a balanced equation for the reaction of glucose. Glucose is blood sugar, C6H12O6. It's reacting with, so you hear that? That's a positive for, it's like an addition sign, glucose plus oxygen. To form is the arrow, and it's forming carbon dioxide and water. Now this pattern is getting very familiar, isn't it? You're recognizing it as a combustion pattern, taking a fuel such as a sugar, burning it in oxygen to release energy. The carbon dioxide that comes out, the water that comes out, and a whole lot of ATP energy if you know your biology. This looks like respiration. A beginning student does very well by practicing with these little lines in front to make you remember where the coefficients go to balance. We use a T-chart to balance. Do the C's, then H's, then O's. Tally up 6 carbons on the left, 12 hydrogens on the left, and 6 oxygens plus 2 more gives you 8 combined on the left side. All right, let's count 1 carbon, 2 hydrogens, and a combined total of 2 plus 1 more is 3 oxygens. Use your C's, then H's, then O's. Let's repair carbons first. Placing a 6 in front of the carbon dioxide also changes the oxygen, so make sure you see that. You have 6 times 2 is 12, plus 1 more in the water yet, so now we're at 13. Got the carbons working. Go down to your hydrogens. 12 on the left and only 2 on the right. So let's place a coefficient of 6 and repair your T-chart. 6 times 2 is 12 hydrogens. Now let's also take care of the oxygens. We still have 12 from the carbon dioxide. 6 times 2 is 12, but now we have 6 more from the water, giving us 18 oxygens. Now, with this example, we have 18 oxygens on the right side. We need a total combined volume, or total combined number to be 18. But remember, there's 6 of them already accounted for. So when I subtract 6, I really need 12 more. I don't want to put a coefficient here because I would change the carbons and the hydrogens, and I don't want to do that. I've got them all behaving. I don't want to put a coefficient there and mess them up. So I want to place a coefficient here that when added to the 6 oxygens present in the fuel, in that sugar, will give me a combined total of 18. 6 of them are already taken up from the sugar molecule, so we need 12 more. I can place a coefficient of a 6 right here so that I could get 6 times 2, that's 12 from the oxygen, plus the 6 from the fuel, and I have now 18. And that balances our equation. A 1 to 6 to 6 to 6, which is our respiration equation. And if you remember, if you reversed it, it would be called photosynthesis. The pattern of change is called a combustion. Now, this skill is a practiced skill. Practice, practice, practice. It is not taught to you by modeling, just, a few examples to give the idea. You have to really put the time in to get good at it. So here's your opportunity. Looking at page 3, you have an opportunity to just sit and practice balancing equations. Come on back to the video when ready to check your work. Pause right now, work to balance these, and then come back. All right, I really hope you took some good time to practice balancing. Letter A takes oxygen and hydrogen. And notice what I'm doing? I'm getting in the habit of showing that I want coefficients in the front of the reactants and products. Hydrogen plus oxygen combine to form water. We will learn that this is called a combination reaction, where things combine to produce a larger product. Combination has just one product. It's the opposite of a decomposition. T-chart, left, right. We want to count H's and O's. 2 H's, 2 O's on the left, 2 H's, 1 O on the right. So you repaired your oxygen by doubling the water. That got the oxygens working, but it also messed up the hydrogen. No worries, you backed up and you placed a 2 and repaired your T-chart. 2 to 1 to 2. 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. Perfect. How'd you do for B? NO reacts with O2 to form NO2. This is also called a combination reaction. 2 or more ingredients combining to make a single product. That's how you'll recognize, when we get that far, you'll recognize a combination, because it's the only pattern of chemical change that has just a single product. It is the opposite of decomposition. Let's tally our chart. We are counting N's and O's in letter B. We start with 1 nitrogen and 3 combined oxygens. On the right side, I have 1 nitrogen and 2 oxygens. So it's not yet balanced. The oxygens need to come up. Let's try a 2. We'll see what we get. That really didn't get me anywhere, did it? Because I can't turn a 3 into a 4. Now my trick for this, when it didn't work by using a 2, when it didn't work first, go to a 3. What I'm saying is, I put 2 in front of the NO2 and I couldn't get the oxygens to balance. So what if instead of a 2, I put a 3 there? Let's go back and just fix our T-chart. I had originally a 1 and a 2. When I put this down, I get 3 N's and 6 O's. All right, I like that because I can put a 3 here and get my N's to work. And 3 plus 2, oh, that's 5. There's 5 oxygens. You know, as I sit here and think, maybe you did this already, what was wrong with my 2? Because now I'm stumped. And yep, I am doing this on purpose, aren't I? If you notice that, I'm really challenging you by making mistakes and letting you think that out. When we started, we had a 1 and a 3. We had a 1 and a 2. And I placed a 2 here. And I had 2 N's and 4 O's. What's wrong with that? As I kind of go through, 2 N's, and 2 plus 2 is 4 O's. You got it. A 2 to 1 to 2 balance that equation. When I said a 2 didn't work, I went to try a 3. It didn't work. I went back to revisit my 2 and convinced myself, yep, that makes sense. I can get it to work. So I went and revisited. So my balanced equation is 2 to 1 to 2 for letter B. Okay, how about letter C? Let's see, we have a methane, CH4, reacting with chlorine to form CH2Cl2 and HCl. Did you create a T-chart? On the left and on the right, we have a carbon, a hydrogen, and a chlorine to tally. 1 carbon, 4 H's, and 2 Cl's. On the left side, let's see, I have 1 carbon, 1, 2, 3 H's, and 1, 2, 3 Cl's. Well, carbons look okay, don't they? So what do we want to do here? How about, shall we try to repair the H's by placing a 2 here and see what happens? I have 2 H's plus 2 more from here. That's 4. I like that. And we have 2 Cl's and 2 more. So that's good. And look what we could do. We can repair the chlorines to get a total of 4. 1 carbon on each side. Check. 2 chlorine times 2. There's 4 Cl's on each side. Perfect. And then, of course, the 4 hydrogens. So here we had a coefficient of 1 molecule of methane, 2 molecules of chlorine, made 1 molecule of dichloroethane, and 2 molecules of HCl. A 1 to 2 to 1 to 2. All right, let's keep practicing. So far when we get going, you might be able to find that you can just go back and forth in your mind and not really need a T-chart. But until you have that kind of proficiency, a T-chart is the way to go. Putting these in little lines help us remember where the coefficients go as well. So we have a left, right to keep track of. We have a nickel, a hydrogen, and a chlorine. We have 1 of each on the left side, 1 nickel, 2 hydrogens, and 2 Cl's on the right side. This one was easy. We doubled the HCl and have everything obeying the law of conservation of mass. A 1 to 2 to 1 to 1 balances that equation. We will learn that this represents a pattern of chemical change known as a single replacement. An element plus a compound, we will call it a single replacement reaction. An element plus a compound made a new element plus a new compound. We'll see that the nickel kicked out the hydrogen. There's the hydrogen all by itself and stole its partner, the chloride. A single replacement reaction. Letter B. We had methane, CH4, plus chlorine gas, Cl2, forming carbon tetrachloride, and HCl. Your T-charts, you had 1 carbon, 4 hydrogen, and 2 chlorine, 1 carbon, 4 chlorines, plus 1 more is 5, and just 1 hydrogen. Well, what about a 4 here right off the bat? Let's see what that does for us. And the reason I said that is carbons are good, so let's go down and repair the hydrogens. And by putting a 4 in front of HCl's, repaired the hydrogens. And what did it do now? Whoops, what did it do now to the there we go, got it. There's 4 chlorines plus 4 more in the HCl. We have 8. Yep, 8 chlorines on the right side. Oh, easy peasy. We can put a 4 there and get 8. A 1 to 4 to 1 to 4 balanced that equation. 1 carbon, 4 hydrogens, and 8 chlorines on both sides of our arrow. Good work. Letter C, potassium chlorate. Oh, you did this in the lab. You took some potassium chlorate and you heated it to force it to decompose. Out came potassium chloride and oxygen gas. Now this is known as a decomposition reaction, a single product breaking down into smaller pieces, a decomp. When we do our tally, we have left and right. We're counting potassiums, chlorines, and oxygens. On the left side, there's 1 K, 1 Cl, and 3 O's. On the right side, the K's and the Cl's, but it's the oxygen that are not yet balanced. I'm going to turn this into an even number. And to do that, I'm going to double it. Let's double the KClO3. And I have to turn it into an even number because there's no way I can get an O2 molecule to ever come out odd, right? It only comes as even pairs. So when I double the left, I get 2 Ks, 2 Cls, and 6 Os. On the right, I can fix my KCls by placing a 2 in front of the KCl. Oh, we got it. Here's a 3, and I can turn that one into a 6. 2 KClO3s decompose to form 2 KCls and 3 O2s. There's your letter C. Letter D, Al2O3 plus HCl yields AlCl3 and water. Let's see, 2 aluminums, 4 guys to keep track of, 2 aluminums, 3 oxygens, 1 hydrogen, 1 chlorine, tallied the left. On the right side, 1 aluminum, 3 chlorines, 2 hydrogens, and 1 oxygen. All kinds of stuff to repair. For no other reason than it's written on the top, I'm going to start with aluminum. I'll do that by placing a 2 in front of aluminum chloride. Fix your T-chart. We have 2 aluminums, and now 2 times 3 is 6 chlorines. All right, that's fine. Let's see. Oxygens, there's 3 on the left. Shall we try a 3 on the right to repair the oxygens? There's 3 O's. Don't forget to repair your T-chart because now there's a total of 6 hydrogens as well. Oh, beautiful. How about a 6 right there? 6 H's, 6 Cl's. You got it. A 1 to 6 to 2 to 3 balances that equation. Do you recognize it? This is a double replacement. Aluminum went to chloride, hydrogen went to oxygen, a double replacement reaction. We'll learn that in the next section. Letter E, aluminum hydroxide plus sulfuric acid. Hydrogen sulfate is sulfuric acid, forms aluminum sulfate and water. You know what? I'm going to give myself a little more room for this one, and I'm going to show you a trick. I'm going to rewrite letter E down here where I have some space. This is what I want to do. I want to write aluminum hydroxide plus H2SO4 yields aluminum sulfate. And now for water, watch what I'm going to do. I'm going to write that as HOH. That's water, 2 H's and an O, but this is why I like to do it. Aluminum went to sulfate, hydrogen went to hydroxide. Notice now when I go to balance this equation, I have 4 characters. This is known as a double replacement reaction. The 2 positive ions exchange places. Aluminum sulfate hydrogen hydroxide, aluminum hydroxide, hydrogen sulfate. Notice the charges kept constant. We just exchanged partners, and now we need to balance. We have to count aluminum and hydroxides, hydrogens and sulfates. Leave those together. Remember that clues. Leave the polyatomic ions together. All right, now let's tally. On the left, there's 1 aluminum. There's 3 groups of OH. There's 2 hydrogens and 1 group of the polyatomic ion sulfate. On the right side, 2 aluminums, 3 groups of SO4. That's the 3 groups taking the unit SO4. There's 1 hydrogen, 1 hydroxide. Let's repair the aluminums first. I'll do so by placing a 2 on the left side. Let's repair the T-chart. Now I have 2 groups of Al, and 3 times 2, there's 6 groups of OH. All right, let's go down to the next character, the OH, hydroxide. We have 6 of them on the left. Let's put a 6 in front of our water. Repair your T-chart. Because now we have 6 OHs and 6 hydrogens. Count these separate. H, OH. 6 H's and 6 OHs. I really just want you to think of water as hydrogen hydroxide. When you're balancing in a double or even a single replacement reaction, this is so much easier than to separate out the O's and the H's. Aluminum's working. OHs are working. Let's get the hydrogens to work. So we have 6 on the right. Let's try a 3 right here. Repair your T-chart. 3 times 2 is 6 hydrogens and 3 groups of sulfate, 3 units of SO4, and we've balanced the equation. 2 to 3 to 1 to 6 balances letter E from our first problem. All right, good work. How about the second set? Magnesium plus HBr yields magnesium bromide and hydrogen gas. 1 mg, 1 mg, check. 1 H, 2 H's. I'll start by placing a 2 in front of the H and in front of the Br. And you know what we've done? We've balanced. When you look at your T-chart, the magnesiums, the H's, and the Brs. There's 1 magnesium. Perfect. There's 2 H's. Oh yeah. And 2 Brs. A 1 to 2 to 1 to 1. Balanced. Here we have CO plus O2 going to CO2. 1 carbon on each side. Perfect. 3 oxygens on the left, 2 on the right. Well, what we'll have to do is to kind of go like this. Let's try, what if we did a 2 and a 2? Repairing the carbons. There's still both 2 carbons. On both sides, and there's 4 oxygens on both sides. A 2 to 1 to 2 balanced your equation. Repetition. I hope you're still practicing. One PB, perfect. 1 S, perfect. 2 O's, 3 O's. All right, so that means we got to get this odd number fixed. 2 leads, 2 leads. 2 sulfurs, 4, 5, 6 oxygens, 6 oxygens. 2, 3, 2, 2. If that's too fast, slow down, stop the video, and count it for yourself. 2, 3, 2, 2 gave us 2 leads, 2 sulfurs, and 6 oxygens. H2SO4 plus NaOH yields Na2SO4 plus, here's my trick, water is HOH. Separated out since it's separate over here. Do you recognize acid-base chemistry? H went to OH, calcium went to phosphate. So, whoops, same one down there, isn't it? Down here, sodium went to sulfate, hydrogen went to hydroxide. You're going to see that same pattern in a moment here. We're going to separate out HOH. So focusing in on letter D. Think of your T-chart now. You have 2 hydrogens and 1 sulfate reacting with 1 sodium, 1 hydroxide to form 2 sodiums and a sulfate and 1 hydrogen hydroxide. Hydrogen hydroxide, that's our water. All right, 2 NAs, let's double the NAs. 2 NAs, 2 NAs, perfect. 1 sulfate, perfect. 2 H's and 2 OH's means we doubled the water. Now, is that too fast? Are you getting so good you can do this with me? HSO4, NaOH. Those are the 4 characters we're balancing. On the left side, I count 2 hydrogens and 1 group of SO4. I count 2 NAs and 2 groups of OH. On the right, I count 2 NAs and 1 group of SO4. I have 2 hydrogens and 2 hydroxides combining to make 2 water molecules. So that's our T-chart for letter E. D, here's E. H3PO4 we'll learn as an acid, starts with an H, phosphoric acid. It's also reacting with a base, calcium hydroxide, CaOH taken twice. See how this is a double replacement? Calcium goes to phosphate. And remember, this is all based on charge. Hydrogen's a +1, phosphate's a -3, calcium's a +2, hydroxide a -1. So we're learning that these balanced formulas just come from crisscrossing charges. Hydrogen's a +1, hydroxide's a -1, so HOH. Same story up here, +1 -2, +1 -1, +1 -2, +1 -1. Those subscripts in the formulas are just simply there to balance electrical charge. I notice there's 3 calciums. That tells me to put a 3 in front of our CaOH taken twice. I see that there are now 6 hydroxides. 2 times 3 is 6 hydroxides. And then I can see that this will require a 2, Ca3PO4 taken twice, gives us 2 phosphates, 6 hydrogens, 3 calciums, and 6 hydroxides. 2, 3, 1, 6, checking your work for letter E. Oh my goodness, I feel so accomplished. We have just practiced balancing equations, and that took us very careful time. I mean, that was 30 minutes of practice. You included pausing your video and practice first. Now I'm going to stop the video here. We'll come back for section 2. Section 3, types of chemical reactions.